Hydropower penstocks are the main arteries of a dam, carrying massive volumes of highly pressurized water down steep, unforgiving mountain terrain. To prevent that turbulent pipe from tearing away from the slope, engineers use massive concrete anchor blocks to pin the steel safely to the mountain. If a single anchor block structurally fails, the penstock ruptures. The result is a multi-million-dollar structural collapse, severe environmental destruction, and immediate project termination. Success on a mountain slope relies entirely on securing these concrete anchors against overwhelming physical force. Behind these massive physical structures is an engineering office, where the calculations keeping them stable rely heavily on fragmented, manual Excel spreadsheets. A senior engineer currently spends hours building and linking the formulas and manually cross-checking the math to design just one block. A single typo or mislinked cell while resolving complex hydrostatic forces results in a mathematically flawed, under-designed block, injecting severe, hidden risk directly into the project timeline. Relying on unstandardized manual data entry for critical infrastructure leaves high-stakes operations dangerously exposed to simple keystroke failures. AnchorBlock Pro is a browser-based Chrome extension engineered specifically to eliminate manual calculation errors through complete automation. By condensing multi-hour engineering tasks into seconds of basic data entry, it aggressively reduces preliminary and final design overhead. The software runs entirely locally on the engineer's machine. Sensitive topographical coordinates and proprietary firm data never leave the local computer. With a single click, it generates a transparent step-by-step PDF report. Every mathematical step and force vector is printed and stamped, creating an instant, mathematically verified audit trail for government regulators and financiers. A slow, high-risk operational task becomes an instantaneous, secure, and perfectly auditable corporate asset. This deterministic physics engine uses the rigorous Alternative Energy Promotion Center, or AEPC, 10-force method to simultaneously calculate 10 distinct forces. At the pipe bend, it captures massive hydrostatic thrust, instantly resolving precise X and Y coordinates along the exact bisector angle. The software then maps the geometric center of gravity, calculating individual lever arms for every force, which pivot perfectly around the upstream toe to pinpoint the exact center of resultant pressure. If the mountain slope is steeper than the soil's internal friction angle, standard equations mathematically fail. The software detects this unstable condition and dynamically falls back to a horizontal backfill formula, maintaining conservative, safe limits without crashing. Complex trigonometric and topological structural resolutions are handled entirely by the physics engine, removing human guesswork from the equation. All calculated vectors ultimately face 3 final critical geometrical tests, evaluated across both expansion and contraction scenarios. First, this diagram illustrates the sliding check. It verifies that the total horizontal pushing forces are strictly less than the friction of the concrete base against the mountain soil. Next is the bearing capacity check. The software calculates the maximum pressure at the toe of the block to guarantee the underlying soil will not structurally collapse under the concentrated weight. Finally, we see the overturning check. The downward resultant force must strike exactly within the middle third of the concrete base to prevent the structure from tipping. Passing these 3 strict limits provides verified mathematical proof that the block will remain entirely stationary under maximum project pressure. We move from a slow, manual process, highly susceptible to arithmetic mistakes, to a mathematically flawless, instantaneous engineering workflow. For the corporate boardroom, this slashes preliminary engineering overhead while simultaneously neutralizing millions of dollars in operational risk. By catching geometrical flaws early, every design is guaranteed to comply with strict structural engineering guidelines long before construction begins. In high-stakes infrastructure, true engineering innovation requires delivering undeniable structural certainty before a single yard of concrete is poured.